Hi, this is Cora Stack again. I'm very interested in investigating AI from the point of view of regulation. So let's try and understand what AI is all about. So this is where I'm now looking at investigating. It's another line of inquiry that I'm looking at. So it's called linear algebra, the hidden engine of artificial intelligence, optimization constraint, and the geometry of governance. So, so what if I told you that the most powerful artificial intelligence systems in the world are not built on mystery at all? What if beneath the headlines, beneath the hype, beneath the language of smart machines, there lies something much older, much more elegant, and much more precise? What if the real engine of artificial intelligence is pure mathematics? Not just any mathematics, but linear algebra, optimization, and the geometry of high dimensional space. In this video, I want to show you that artificial intelligence is not magic, or indeed artificial inverted commas. It's not an unknowable black box. It is at its core a mathematical system. And once we understand that, I think a far more important question emerges. If mathematicians are being hired or brought in to design the algorithms, the optimization systems, and in particular the constraint functions that shape artificial intelligence, are they also being brought in to regulate them? I mean, I don't hear of this at all. It's very, very concerning that we don't hear that there are teams of mathematicians being hired to regulate AI. We don't hear that at all. But because if not, then we may be building systems of enormous social power without bringing sufficient mathematical expertise into the institutions meant to oversee them. Artificial intelligence is often described as a revolution driven by vast data sets and immense computational power. Now, I'm investigating this at the moment, so I'm trying to understand it better. But this has come as a bit of a surprise to me and a bit of a shock. This is true, but only partly true. Data alone does not create intelligence. Computers alone do not create intelligence. The real underlying structure of AI is mathematical. At the heart of modern AI systems are ideas developed long before modern computing systems existed. Vectors, matrices, all removed from the Project Maths curriculum years ago when I strongly advocated for, against enormous pressure, that this was a real unwise move by Irish, by the NCCA. Very, very unwise. And here we are. Vectors, matrices, eigenvalues, linear transformations, optimization, and constraint optimization. And indeed, a lot of this was being brought back in a fantastic review paper by the NCCA, and it was cancelled or abandoned. And the current format of what they're doing is it's shockingly poor compared to their original one that they abandoned years ago. Because of inverted commas vested interest in view of this in particular. So these ideas were developed in the 18th and 19th centuries by mathematicians such as Gauss, Lagrange, Cauchy, Grassmann. I wasn't aware of. He was a teacher, so he hasn't got the credit he deserved because he wasn't sort of our university professor. But in fact, he was. He actually made major contributions to the development of linear algebra, in particular with regard to linear independence. Cayley and of course our own William Rowan Hamilton. These mathematicians were not building search engines, machine learning systems, or large language models. They were pursuing pure mathematical truth. And Science Foundation in Ireland, as I understand it now, I don't want to unfair to them, have deliberately excluded pure mathematics from their research funding for years and years and years. And here we are, at the core of artificial intelligence is pure mathematics. It's yet today because their ideas form the invisible architecture of some of the most powerful technologies in the world. So who's making the decisions that pure mathematics should not be funded in an age where artificial intelligence is almost entirely dependent on pure mathematics that was developed centuries ago? So why is linear algebra so central to AI? because once information is converted into numbers, it can be represented as a vector. And we don't even have vectors in the current project maths leaving cert at ordinary level or higher level anymore. We don't have the concept of a vector. It's been removed. A word can become a vector. An image can become a vector. A sound can become a vector. A sentence, a financial profile, a medical scan, even patterns of human behaviour, all can be embedded into high-dimensional vector spaces. Once data is represented this way, AI becomes a geometric problem. So when we begin by asking mathematical questions: how close are two vectors? How similar are they? Which directions contain the most information? How do we transform one representation into another? How do we compress information? How do we optimize the system to perform better? This is the language of linear algebra. The dot product measures closeness, or it's termed alignment in AI. Norms measure size. These are normed vector spaces, Euclidean vector spaces with norms, and distances measured, similarity or distance between two vectors. Orthogonality helps us identify independence and remove redundancy. These concepts, projections helps us to find best approximations. These are all, and matrices perform transformations. This is not peripheral to AI. This is AI. One of the most powerful ideas in linear algebra is that a matrix is not just a rectangular array of numbers. And that's what you start with. The most important aspect of a matrix or property is that it is the transformation of space. When a matrix acts on a vector, it changes that vector. It may stretch it or compress it. And that's everything got to do with eigenvalues and eigenvectors. It'll rotate it, shear it, or move it into a new representation. This is exactly what happens inside modern AI systems. At each layer of a machine learning model, vectors are transformed by matrices. A simplified layer may be written as z equal to wx plus b, where x is the input vector, w is the matrix, b is the translation vector, or often referred to in the AI language as the bias vector, and z is the output, a transformed output. That simple mathematical form lies at the heart of neural networks. So when people talk about AI as if it was mysterious, it is worth remembering that much of what is happening is repeated matrix transformation in very high dimensional spaces. The scale is enormous, but the mathematics is classical linear algebra. But AI does not simply transform data, it also learns, and mathematically learning means optimization. A model begins with parameters, often millions or billions of them. Its scale is unbelievable. These parameters determine how the system transforms input data. The goal of training it is to adjust these parameters so that the system performs better, and that's happening all the time. But this is done by minimizing a loss function, a function that measures how wrong the model currently is. So the model is in effect trying to solve a problem of the form minimize L of theta, which is called a loss function, where theta represents the parameters. The gradient tells the system which direction increases the loss most rapidly. So to improve performance, the model moves in the opposite direction. This is the core idea behind gradient descent. So this is all advanced calculus, and this is all proposed to be put into the review of project maths in a very an excellent consultation document by the NCC, which was abandoned years ago in 2014 or shortly after that. It's very, very sad indeed, given what we're now dealing with, because the regulation really requires top-class mathematicians, and they're just not there. We're not training them. They've been brought in from abroad to design the systems, but we need top-class mathematicians in Ireland to regulate that constraint function, to ensure it's regulated, and for governance governments to have laws in place where people can go in and regulate that constraint function in whatever way is possible, so that it does not transfer risk unfairly onto the majority of people, as it seems to be doing at the moment. The squeeze middle. The system is repeatedly asking, how do I adjust my parameters to reduce error? And the answer is given through mathematics. So the thing I'm really focusing in now is the constraint function, the hidden architecture of decision making. Now we come to something, in my opinion, which is the most important part of it all in terms of the regulation. Just from my initial investigations, we come to something much more important and much less widely understood. I mean, I've been, around, and I've seen, a number of these conferences about AI. I rarely see mathematicians talking about this. Or, I mean, I wouldn't say rarely see it, but I don't really. It's all computer science people. There are very few mathematicians involved in this. And it seems to me they should be centrally involved at the policy level, at the research level, and SFI aren't giving any money to pure mathematics. Or over 20 years they've squeezed. And this is not just unique to Ireland, it's worldwide. So, this kind of looking down on pure mathematics is there was no relevance. And I've been saying for years this is very poor vision. So optimization in AI rarely happens in a completely free space. It usually happens subject to constraints. This is the key thing. I mean, this isn't rocket science if you understood it. This means the system is not just trying to find the best solution. It's trying to find the best solution within a restricted region. But this is the mathematics of constrained optimization. In simple terms, instead of solving minimize or maximize fx, we solve minimize fx subject to a constraint, which we usually write g of x equal to 0. The constraint function gx restricts what solutions are allowed. This changes everything. Because once you change the constraints, you change the geometry of the problem. And when you change the geometry of the problem, you change the outcome. This is one of the deepest, this is what I've discovered, in the last few months trying to figure all this out. This is one of the deepest structural truths about AI. The system's behavior is not determined only by data. It is also determined by what objective function has been chosen, what constraints have been imposed, what trade-offs have been encoded, and what kind of outcomes have been made mathematically admissible. This means that human judgment is built into the system at the level of design. For these four, what objective function has been chosen, what constraints have been imposed, what trade-offs have been encoded, and what kinds of outcomes have been made mathematically admissible. This means that human judgment is built into the system at this level of design, not only in the data, not only in the interface, but in the mathematics itself. Why this matters for society. Now let us think about what this means beyond the technical world. If an algorithm is used to rank people, allocate resources, assess creditworthiness, evaluate risk, prioritize applications, influence hiring, all of this, going for a job. Sure, does it all go into an AI algorithm? Guide policing, filter educational opportunities, or shape what information people see, then the structure of the optimization problem matters enormously, hugely. The choice of constraints may determine who is included, who is excluded, who is prioritized, and in particular, who is disadvantaged. And yet the public discussions of AI often remain very superficial at a surface level. We hear a huge amount about big tech, data, scale, innovation, speed, disruption, but far less attention is given to the mathematical architecture that actually governs outcomes. And this is a very serious problem, because if policymakers and regulatory institutions do not understand the mathematical structure of optimization and constraint, or aren't even funding research into this, or funding pure mathematics departments, and to ensure that they are on a par with other departments in terms of funding, resources, going to conferences, all of that kind of thing, then they may not fully understand the systems they're trying to oversee. Large language models provide a perfect example. These systems can appear astonishing. They generate text, answer questions, summarize documents, and produce seemingly fluent responses. But at their mathematical core, they're still operating through vector representations, matrix transformations, and optimization over very high dimensional vector spaces. Words are embedded as vectors, so it really galls me that vectors were removed from the Leaving Certificate. It absolutely, when I see this, I'm shocked. Relations and matrices, I'm absolutely shocked. Relationships are measured geometrically. Transformations are applied layer by layer. Parameters are adjusted through optimization. So even in the most advanced AI systems, the foundations remain linear algebra and optimization. This is what we were arguing in our papers on major flaws in project maths, and project maths isn't challenging enough, this does not make them trivial, but it does make them more understandable. And once we understand that, we're in a better position to ask serious questions about accountability. So education and mathematical literacy, this also has major implications for education. Again, I'm just investigating this at the moment, so I'm at a very early stage, but I think looking at the constraint and looking at who's designing those constraints, who's paying for that design, and are the regulatory bodies, are they sufficiently mathematically trained to be able to see, to be able to properly, engage in the type of regulation of these systems if they do not understand the basic mathematics involved in here. So for many years, topics like vectors, matrices, eigenvalues and optimization were seen by some students as abstract or remote, and indeed by many of Ireland's major funding agencies and policymakers. But today they sit at the centre of the modern knowledge economy. And we said that. We said it, and this is what we said. Linear algebra is no longer a niche subject. It's one of the foundational languages of artificial intelligence, data science, engineering, economics, and computational science. If we want future generations not just to use technology, but to understand it, critique it, and govern it, then we need much stronger mathematical literacy, not only for specialists, but also across institutions, because the future will not merely belong to those who can code, it will also belong to those who understand the structure of the systems being built. And this brings me to the central governance question. Mathematicians are already being hired to design AI systems. They are helping to build the algorithms, the optimization frameworks, the embedding systems, the loss functions, the regularization methods, and in particular, the constraint structures that shape how these systems behave. They are in many cases helping to build the engines, but are they being hired or brought in to regulate them? Are mathematicians sufficiently present in regulatory agencies, oversight bodies, ethics frameworks, standard-setting institutions, government advisory groups, and public policy design? Because if they are not, then we face a profound imbalance. We may have mathematical sophistication at the point of invention, but totally inadequate mathematical scrutiny at the point of governance. And this is dangerous in inverted commas. Why? Because regulation that does not understand optimization cannot fully interrogate optimization. Absolutely. Regulation that does not understand constraint functions cannot fully examine how outcomes are being shaped. Regulation that does not understand the geometry of these systems may end up regulating appearances rather than structures. And AI is structural. Its power lies not only in what it outputs, but also in how its objectives and constraints are mathematically formulated. So perhaps one of the greatest governance questions of this time is this: if mathematicians are trusted to build the systems, why are they not equally central in designing the frameworks that regulate them? We do not regulate financial derivatives without quantitative experience. We don't regulate pharmaceuticals without scientific experience. We should not regulate artificial intelligence without deep mathematical experience either. This does not mean every policymaker must become a mathematician, but it does mean that serious governance of AI requires direct access to people who understand the mathematics of optimization, linear algebra, high-dimensional geometry, objective functions, and in particular constraint structures, because this is where the real architecture of power often lies. And unless that architecture is understood, oversight will remain incomplete. So the challenge before us is not simply to build more powerful AI, it's to build wiser institutions around it. Institutions capable not only of encouraging innovation, but of understanding the mathematics that governs its consequences. This is not merely a technical task, it's an educational task, a political task, a democratic task, and increasingly a moral one. Closing. Artificial intelligence may be one of the most defining technologies of our age, but its foundations are deeply mathematical. I mean, I'm stunned really, when I started investigating this. Linear algebra gives AI its language. Optimization gives it its learning mechanism. Constraint functions help shape its behaviour, and governments must now catch up with that reality. If we want responsible AI, we need more than innovation. We need mathematical understanding at the level of policy oversight and public accountability. And thank you for watching.